Yeah, thank you very much for the opportunity. My name is Sven Jensen. I'm working for the company Dürr. So what we do is, in fact, we have a system, a technology to create value out of heat or waste heat. And this is what I want to present today, the application to the pyrolysis industry or to the biochar industry, which uses pyrolysis for the production of biochar. I'm working in sales here for this product with Dürr. And by education, I'm thermal engineer, process engineer, and I'm working now for 7 years here for the company Dürr. So, this is a short agenda. I will briefly tell some few words about the company Dürr so that you just know what is behind. Thereafter, I will explain about the technology, what is this in general terms, ORC technology, what it means, but also how we have modified or how we are applying this technology for actual products and solutions. And then, more specifically, I will talk about how we apply this to the biochar industry. And then in the in section 4, we have I will show some references, and in the end, I want to give a short summary. So if time is short, then I will fly through the references. This will be recorded or maybe even distributed, so you can see then the references later. So the company Dürr, we are in Germany, a little bit north of the city of Stuttgart. It is a family-owned company, basically one of the kind of famous German Mittelstand. Dürr is constituted of basically 5 sections with 3 names, brand names or company names. That is Dürr itself, Schenk and Homag. Homag is in the machinery and plants for woodworking. Schenk is a specialized machine manufacturing company. And then within Dürr, there are 3 columns left, and that is mainly automotive. So this is on the left part. It's painting, gluing systems, has a lot to do with robots and so. And with painting, you can imagine there's also a problem of the exhaust gases. And this is how this section or the division Clean Technology Systems came into life, whatever, 70 years ago, to treat exhaust gases, grew and expanded. And then roughly 15 years ago, also, there was a expansion into other fields, more like decentralized power generation, what we are part of. So the Dürr Group itself has given itself a sustainability policy that concerns the scope 1 and 2 targets, of course, but also scope 3. And this is then basically our product stands for that, to improve the efficiency on the side of the customers. So now about the ORC technology. What is it? ORC stands for Organic Rankine Cycle. So that is similar to the Clausius-Rankine cycle, what is also known as the typical water steam cycle. So what we all might have learned at university school or university, so what is basically happening in a power station. Coal-fired power station. So you heat up water, you have steam, you send it to a turbine, you condense again, and you close the cycle. And we do very much the same, only that we use an organic media instead of water and steam. So here on the left-hand side, we have a short overview, a sketch, how it works. We have a main heat exchanger where we capture the heat. So we call it also evaporator, where we heat up the ORC working media and we evaporate. So it's really a vapor, even though it's an organic media, it's vapor. We send it to the turbo generator, and this is then the place where the electricity is produced. In order to close the cycle also here, we need to take out the energy, thermal energy, and to transform or transfer the ORC working media into a liquid state again in order to pump it back to the evaporator and to close the cycle. And then we see here one box in between, and that is the recuperator, and that's just an internal heat transfer in order to improve the efficiency. So just summarize again, we take heat in, we have to take heat out again, out of the black box, so to speak, condensing heat. And by doing that, so from a high temperature reservoir or level to a lower level, this is how we generate electricity. Here on the left-hand side is then the ST diagram. This is for the engineers among us. And you can see basically and compare these different stages to this sketch on the left-hand side. Here we see on the right-hand side some pictures how those systems look like in real life. So we have taken the approach to erect these things or to mount them on a steel frame. That means we have everything modular fabricated as a module. So the heat exchangers on the skid, as well as all the ancillary, and also the electrical cubicle and control cubicle, as you can see here. This leads to easy transport, of course, to the customer side, and then it's easy for installation and commissioning. With the control cabinet, we have the full automated function and the possibility to access also from remote. Then our systems are possible to take different sources of heat. So may it be the heat carried with exhaust gas, or with thermal oil, steam, or hot water. And then, because this stands also for certain levels of temperature on the incoming side, so we have corresponding ORC working media. So in total, we work with 4 different working medias. Here we see now the same sketch, or a similar sketch again, what we had before. So here in the central gray area. And with this picture, we want to differentiate again between the low temperature application, how we call it, and the high temperature. So low temperature, as according to our definition, is when we receive the heat in the form of warm water or steam. And high temperature means that we receive the heat, thermal oil or exhaust gas. So the cycle as such is the same. I mentioned already we have different ORC working media, but there's one major difference. If we receive the incoming heat on a lower temperature, then basically it's necessary also to get rid of the heat on a as low temperature as possible. So in practical terms, it means that we behind the condenser there is a cooling tower type of a cooling tower or dry coolers. So basically just horizontal laminar coolers with a fan. So you dissipate the heat into the air. When we talk about high temperature application, so we have thermal oil 300 degrees, for example, or exhaust gases 500 degrees, for example. Then we can run this, what is here in the gray area, in a different way. So we can operate the condenser at elevated temperatures, 90 degrees up to 95 degrees Celsius. And then we can connect on this side, not a cooling tower, but a hot water loop. So basically all the condensing heat, what we need to extract from the ORC, we can push into a heating system, or this can be used for other purposes. This is quite important also for industrial applications. I will explain also then in some further slides later. This is just 2 pictures of our turbo generator. We have a completely capsuled system. So the turbine here on the silvery part and the turbo generator in the blue part is enclosed in one common casing. So we have one shaft, one common casing, and that is important to mention because This makes sure that we really talk about a completely tight system. So we also talk about the hermetically sealed generator. So we are working with natural ORC or natural hydrocarbons. And for that purpose, or for that reason, it is really important that we keep that working media inside our system. The entire system, as we saw in the earlier picture, is classified as a technical tight system. Here we see basically the product range, what we can offer. So these digits like 50, 70, and so on, up to 500, that stands for the electrical gross production of the individual modules or systems. Many of the systems, so these pictures, what we see here, they are suitable for capturing hot gases. Those here in the lower row are designed for thermal oil as heat transfer media. And then when we talk about big units, so 250 to 500, and when we are talking about hot gas as the heat transfer media, then we need relatively large heat exchangers. This is basically the box, what you see here, a standing box. And then we cannot continue with the system as we started to have everything mounted on one module, but then we are with half a foot into the plant engineering. And then we have 2 or 3 shipment items in order to have the full installation at the customer side. So this was about the technology and about the product, so how we turn the technology into real products. And now I will explain a bit about the application to the biochar industry. Biochar industry, or the aim is to produce biochar. So we have basically a feed in from biomass. I just made it very simple. We have here material handling, and then clearly in the center, the carbonization plant. We need to put power in, electrical power, for whatever motor is there. And then in the end, we gain biochar. And then depending on the type of the system, you have a filter or not, and you have gas cleaning or not before you send the gases, the burnt syngases to the stack. Typically, and now you will see more of these figures in blue, and I just took some very general figures. So typically, the organic matter has about 35% water content. Some plants tolerate this much of water. Some other plants rather would like to have less. So for my purpose, I defined that it is better to have a dry biomass entering the carbonization plant. So dry biomass with only 10% residual moisture. And in order to achieve that, a drying step shall be necessary. So you need to introduce some heat in order to evaporate the water to get rid of it. So basically 25%, the difference between the two in mass percent, you need to evaporate. And then basically the rest stays the same. The carbonization plant basically operates better because it needs to evaporate less water. Because all the water you take out before the carbonization plant, you do not have in the stack in the end. So, and then the ORC system, so the carbonization plant produces the syngases, and either the incineration is part of the carbonization plant itself, or you have a separate combustion chamber. But basically, it produces hot gases. So whatever, 900, 1000 degrees. So similar to normal just gas incineration. And this is now how we can connect the side plant ORC system to it. The filter can be before or after if a filter is necessary, but the point is the ORC really receives the hot gases directly. So we can take them at temperatures around about 500 degrees Celsius. I mentioned that normally it might be higher than that. And so what we do is basically we recirculate the flue gas, what we have cooled down in the direction of 200 degrees Celsius, we recirculate to the front and mix it with the hotter gas. And so we achieve basically the desired temperature of about 500 degrees Celsius. And now comes into play the specific benefits which I tried to explain before. So the ORC can not only produce power, but it can also provide secondary heat. So let's talk about the power first. So power generation of the ORC is clearly the ORC is producing a certain defined amount of power depending on the heat input, and according to our knowledge or experience with OEM manufacturers of carbonization plants, roughly 30% of what we produce then goes to, is consumed on site for plant use. But that includes then basically everything. So that includes the self-consumption of the ORC plant itself, as well the motors of the carbonization plant I mentioned before, but also, for example, in material handling and or drying, you have different motors and so on, electrical consumers, and all that together, then we are very roughly in the range of between 20, 25 to maximum 40%. And this means you still can sell roughly 70% of the electricity, what is produced by the ORC, to the grid. And the second benefit is the secondary heat. So here you can feed back the heat to the drying to the drying system. And here again, some typical figures that roughly 40% of the secondary heat is then necessary to perform the drying. And still you have about 60% of the heat available to sell to third party. And whatever it is, maybe other drying purposes or for any other industry, or for example, you can, in this setup, you can also send this secondary heat to a district heating network, for example. And now I give the values for a biomass plant or input of roughly 15,000 tons per year. If we have that much of mass flow available, then my assumptions and rough calculations show that we could produce up to 5,000 tons of biochar. And with this energy content, of the difference and the syngases which are produced and burned, we can approximately generate 500 kilowatt electrical power. 150 goes to the own consumption. And we have 2.3 megawatt of heat, of which maybe, now 400, 500 kilowatt goes to the drying, and then the rest, whatever 1.5 megawatt is still available for district heating. So this is basically the summary of how the ORC can be integrated into the whole entire setup of a high efficient biochar production plant. We are lucky that we have already some contracts with relevant partners, for example, with the German company Pyrolysis. So we have already 2 existing contracts for 4 units in total. And here you see how the ORC is really completely integrated into the delivery or the parts of the company Pyrolysis, the pyrolysation plant. And basically just what I mentioned, we receive the hot gas from the burning of the syngases. We produce electricity and we provide hot water. And here in this project Grevesmühle, also known under the name, again, help me, Baltic Sea carbonization plant. Here the heat is basically sent to the municipal district heating network. Another German company, the company CTS, Carbon Technik Schuster. So they asked us, we have delivered a plant. Basically, again, the same system, a little bit larger in this case because the system itself, the carbonization plant is larger, but basically the same setup, and also the secondary heat is used for other purposes. And once again, another company, a German company, but the site will be in the US, close to Salt Lake City. It is the German company Carboforce. And here we are delivering a big unit, so the Cyplan ORC 500, to be combined with the air system. So now, can somebody just tell me what is the time? Unfortunately, I do not have a watch with me right now. How many minutes? Where
Yeah,
are we?
you're about through, but you know it's okay if you take 5 more minutes. That's not an issue.
Yeah, okay. Then I make this very quickly. So these are references. We have around about 65 installations in Germany and some other 10 plus in Europe, mostly Central Europe, and some other installations abroad. We have been very active in the area of biogas, where we receive the exhaust gases from internal combustion engines. Here are some typical examples where the customers were happy, could generate nice returns on their investment. But also another example here, biomass. It is an industrial customer producing basically wood-based products. And he has a lot of waste cut off and dust and so, and he's incinerating on the spot, giving us the heat as thermal oil, and then we run a big ORC unit here. But also this technology can be applied in the industry, classic or heavy industry, steel industry, for example. In this case, we take the exhaust gas of a reheat oven. Okay, in this case, it is gas fired, so natural gas, but basically just to show that these technologies can be applied to different sources. Yeah, here we produce 500 degrees, just a little bit of the plant performance. So then summary. So we have a product, but we understand ourselves not only as a simple machine engineering company, but we can also basically tailor to a certain extent our unit to the needs of any heat source. So this is basically an invitation if ever there is a company out there, a carbonization plant, who has not yet thought about the use of the waste heat of a carbonization plant, that we are happy to well get into exchange. We tailor certain pieces of our equipment. We do the engineering, and then clearly the fabrication, integration, commissioning, and then of course we also offer this service for these plants wherever it may be. The benefits, just very short. So as we use waste heat, per definition, the electricity is CO2 free. That helps also for the balancing of the basic negative carbon credits. Our working fluids have a very low or no ozone depletion potential and a very low global warming potential. Clearly, the generation of electricity on the spot can reduce the electricity bills of the customer and leads to a higher independence from the grid. And the condensation heat, as explained, can be used for subsequent usage or purposes. And in some countries, clearly depending on what is the regime, the ORC can be basically a trigger for receiving subsidies and or tax reduction. So this was my presentation. Thank you very much. And yes, please ask questions. I'm very eager to enter into a discussion.
Thanks a lot, Sven. I think with this slide, you answered the question of Marshall, who was asking for contact information. So I think with this, you should have what you need, Marshall. There was a question from Iduo, I think I hope I pronounced the name correctly, which was, can you tell us more about the corrosivity of the syngas? So I suppose in the case of the biochar applications, the syngas is consumed, let's say, and you receive the exhaust gas.
Yes.
And this is then passed through a air slash working fluid heat exchanger.
Yes, correct.
And how does that work with the heat exchanger? Do you have issues there with corrosivity or with maintenance of that heat exchanger?
Yeah. So corrosivity is basically, we talk about sulfur and or chlorine.
Okay.
And when in most applications so far we experience, they are using more or less a natural biomass. So that means wood chips or similar. And yes, there's a certain small amount of sulfur, but that's basically not in a range what really harms the installation. And clearly in the temperature range where we are, so around about above 160 degrees, you do not have problems. You do not have problems with sulfur. So if ever, then we only have an issue during startup or shutdown.
Mm-hmm.
But our unit basically likes to run continuously. So from our side, we only require one maintenance once a year, so one shutdown basically. Depending on the pyrolysis plant, there might be some more shutdowns, but still that's okay. And you can encounter, for example, with the help of preheating, when it's really cold, when you're heating or starting up from ambient temperature in order to reduce the risk. So in a nutshell, or summarizing, sulfur is not really an issue. So this can be handled. Chlorine is another issue. So here we have to look closer. So when the biomass comes from sources very close to the seaside, clearly we have to look at the analysis. So what is in the biomass, or rather, what do we receive as chlorine in the flue gas?
Mm-hmm.
And here are certain limits. Here we need to discuss more in detail. But from my view or experience, it's really seaside biomass, as I said, and or if you have quite a lot of mixed or polluted kind of biomass. So when you have plastic in it or other things which shouldn't be there. When we are rather in the area of waste. Okay. And then another thing, what is not really corrosion, but what has an influence is dust. And here it very much depends on the technology of the biochar producer or the pyrolysis system. So some systems, they deliver very low dust content. So really there we do not have an issue and we do not have clogging and so. Mm-hmm. Some others, they can limit, but still we have a low to medium amount of dust. Then we have to add some cleaning devices, what makes it a bit more complicated. We have to oversize and so, but it can be handled. Okay. Only if we really have to handle very high dust burdens, then yes, that becomes then more an issue, or it becomes more costly. Yeah. But basically it's possible to handle.
And are you actually using syngas directly, so cooling the syngas, or are you using the exhaust gas from the consumption of the syngas?
We use the combusted. I mean, the syngas after combustion.
Okay. Right. Yeah. Understood. Yeah. And there are questions around, the sort of price point and examples of, the price or the production cost of electricity per kilowatt hour, for example, produced, and delivery times. Typical delivery times. You can use, I don't know,
delivery times.
You demonstrated 4,000 tons or 2,000 tons in that range as an idea.
So delivery times for the smaller units are in the range of 9 to 10 months. And for the larger units, then we are basically in the range of 1 year. Specifically, when it is really with a new partner or a new installation, then simply there needs to be a little bit period of engineering upfront. In terms of cost, now we have 6 different sizes. We have different heat transfer media, and so here I ask for I'm sorry that I will not now say one number or a figure, so any price. So please send me then more specific information. So what really is the heat source? What temperatures are we talking about? And also the other parameters, as just mentioned before, dust burden, yes, no, all of that is really the influencing how much the installation costs. And then I or a colleague of mine, we will answer relatively quickly, and then we give first indications. But it's in this frame, I guess it's no use to throw out any number, because it might be way too high, way too low. That's because the application is so wide.
Sure. And one last question quickly before we switch to Mari. What's the smallest unit that you supply and that you have built?
Yeah, so the smallest one produces 50 kilowatt electrical power, and that requires roughly 300 kilowatt of thermal input. So these are numbers which you might remember, and then of course the biggest unit, single unit what we offer, so the 500 kilowatt is just 10 times as much. So then we are around about 3 megawatt of heat input, and then we are producing 500 kilowatt of electricity.
Okay.
And the other 4 units were basically in between.
Okay. Great. Thanks a lot, Sven, for your presentation. And this is all the time that we have for today. But if anyone has follow-up questions, you have Sven's details here on the slide, so make a note of that. Otherwise, the video, the recording is going to be made available anyways through the Green Cloud webinar website.
Okay.
Thank you, Sven.
Perfect. Thank you very much.
Thanks.